Yes, hallelujah. Thank you, Marcus, for noticing this. So yes, please be kind and respectful to each other, and hopefully we'll all have a great time. The materials of this workshop are distributed and were developed and can be distributed following the Creative Commons license, meaning that you can share it with anyone. You can organize your own workshops using those materials. You can adapt it in any way you want. And we strongly encourage you to do this. Because it is essentially what we are trying to do here, to spread the knowledge of how to develop better software in the astronomical community. And if you will want to organize your own workshop, we are always welcome. You're always welcome to ask us for some support, and maybe we can do it together. And today's materials were prepared by quite large and international team of developers from Europe, from United States, from India, and from many other places. And a lot of names here are our core developers who have been doing this for quite some time now. So huge thank you for everyone. And a special thanks to the Tomislav Juru, to the Bura, supercomputer Bura team, who kindly agreed to allow us to use their supercomputer time for practicing the exercises of this workshop. Despite the fact that Bura should be in maintenance right now, because it is mid-August, and most people are actually on vacations and most supercomputers are doing maintenance. But Tomislav Jurkic and Gordon Yanes kindly agreed to assist us. So they will be talking today a little bit about Bura, and they will teach you some of the episodes. And we are very grateful for the support. So this workshop, as I said, we will be practicing on HPC Bura, and the instructions about how to log into it were sent to you via email. So hopefully you all were able to log in without issues. If not so, then please let us know as soon as possible, for example, in the chat, and maybe we will be able to assist you in the next few hours. And we assume that you are going to follow the materials and the lectures along the way. So if the instructors are coding something, if there are exercises, please do these exercises because they're important for the next step. So try not to miss it, despite the fact that we are recording this and that the materials are developed in such a way that in theory they should be understandable even if you read them on your own. For real-time communication, feel free to use the chat or just raise your hand. And there is a schedule for this workshop that was sent to you once again via email. So today we are covering the introduction to HPC in general. Then we will talk a little bit about which HPC facilities are available to the LSST community. Then we will get familiar with the HPC Bura and try on how to use the command line interface commands for running around Bura, inspecting your files, and running Slurm, which is a job management, job manager program, one of the most common being used in various HPC facilities. And tomorrow we will switch to a more hands-on exercises with some practical coding examples, testing how different code is developed for CPU or GPU implementations can be executed, and what is the difference in development for these different techniques. A word of note here, so despite the fact that Bura has GPU nodes, currently they are offline because see above, it is maintenance time. So we won't be able to run GPU examples on Bura itself. However, we are going to go through them using one of our personal computers. So one of our, probably it's going to be me who will share the screen and walk you through what we are doing when we are developing something with NVIDIA GPU cards. And if you have a GPU on your own laptop, then you can run those exercises as well. So there is some practical moment to this episode as well. And once Bura is fully functional, you can ask Gordon and Tomislav to save your accounts, leave your accounts active for some time. And then later you will be able to practice this on Bura with its full functionality. You will also require certain materials for these tomorrow's sessions, but so the link is in the slides that I will share in the chat in a second. but also this link is present in the lesson materials link to which was sent to you via email. So when you will be following the materials at the right moment, you will have this link and you will download it during the episodes. And that would be it from me. And the first session, the first episode is actually the introduction to HPC in general. And I believe Riley is going to be teaching this. Am I correct? Okay. So please, Riley, the word is yours. The floor is yours. Also the word maybe as well, hopefully. So yeah, please go on.
Awesome. Thanks for that introduction, Alex. I'll go ahead and share my screen.
Can you please move your microphone a little bit because it is a little bit damped?
How about now?
I mean, we can hear you, but not very well.
Okay, I'm just using the built-in microphone. Let me see. Oh, wait, hold on. How about now?
Great, much better. Thank you.
Yeah, okay. Sorry about that. I was using the wrong mic. Okay, great. So like Alex said, I'm going to be starting us off here with giving a bit of background information for high performance computing that might be new information for folks that haven't ever done any kind of work with an HPC before. So this section...
Riley, sorry to interrupt once again. Can you please increase the scale of the web page a little bit?
Yes. Oops. Let's see if I zoom in, is that okay?
Yeah, much better. Thank you.
Great. Yeah, so this section should take no more than 20 minutes. There are no exercises for this section. It's just going to be me yapping at you for a bit. So this section is going to cover some kind of core concepts like sequential versus parallel code execution, different types of computer and network architecture, different types of parallelization and how data storage works on an HPC. Just so we get a sense of how the facility is organized and the proper way to use it. Okay, so the types of computation tasks that I think most of us are used to are sequential processing, where instructions are executed like one after another. And this is the default paradigm in most programming languages. So for example, like when you run a for loop in Python, every loop gets executed one after the other. But for larger problems that involve a lot of tasks, where sequential processing might take a really long time, it can be more efficient to exploit the parallel nature of most modern processors, which are designed to execute multiple processes at the same time. So like in the figure here, you have information rather than being executed on the CPU one after the other, you can have multiple different tasks that are executed at the same time. And so this parallelization of data processing has become increasingly essential as our computational demands grow. There's lots of scientific tasks that rely on parallel computing. And high-performance computing, HPC, this is where parallel programming, hardware infrastructure, and systems administration all come together to make this stuff possible. But the efficiency of high-performance computing clusters depend on their architecture and their network architecture. So we're going to talk a little bit about different types of computer architectures. So there's kind of two broad categories of computer architectures, von Neumann and Harvard. And so in a von Neumann design, you have four important components. You have an arithmetic and logic unit, a control unit, a memory unit, and input and output devices. So the ALU retrieves data from the memory unit, performs calculations, while the control unit interprets those instructions and then directs the flow of data, like in this diagram. But in this architecture, there's a performance bottleneck that's due to a limitation in data transfer bandwidth. because the memory unit stores both the data and the instructions. So a partial solution to this bottlenecking was the modified Harvard architecture, where the instructions and data are actually separated into two different memory spaces. So a hybrid approach combines the performance benefits of Harvard with the flexibility of von Neumann. So there's three components that really quantify how powerful a computer is. So you have the CPU, your central processing unit, which is typically quantified by a clock speed, which determines like how many instructions the CPU can execute in terms of like cycles per second. So a CPU with a clock speed of 3.5 gigahertz does 3.5 instructions per second. And many CPUs have multiple cores, and this is what enables the parallelism of handling multiple instructions simultaneously. Another important factor is RAM, or random access memory. This is the computer's short-term memory, which stores the data that you need to run applications and open files. And having faster RAM just helps data move around more quickly. And then larger RAM capacity helps the CPU handle more complex instructions. And then unlike RAM, the hard drive is used for long-term data storage. And they're characterized by capacity and performance. So bigger drives can hold more data, obviously. Hard disk drives tend to offer more capacity but are more cost efficient. And then solid state drives overall tend to provide better performance and reliability. So the laptop that you're on right now probably has between 8 gigs and 32 gigs of RAM, 4 to 10 CPU cores, and a hard drive that could store maybe up to a terabyte of data. But if you need to process data that's a data set that's larger than a terabyte, or you have a really computationally intensive simulation that needs a lot of RAM, you might need your computer specifications might not be sufficient to that task. And so in that case, you would rely on many computers that are networked in parallel. So when we're talking about parallel computing and parallel processing architectures, Flynn's taxonomy is a helpful way to understand the different categorization of computer architectures. So this is based on these four terms: SIMD, or single instruction multiple data. So you can combine these letters to form four different main architectures. So SISD, that's single instruction, single data, a traditional serial computer like the ones we're probably used to. And that does one instruction at a time on a single piece of data. So, just running a kind of default Python program, for example, would be on your laptop would be SISD. Now, SIMD is single instruction multiple data. So this is a parallel architecture where you have multiple processors. They all receive the same instruction, but each works on a different piece of data. And so this approach enables large data parallelism. And one example of an SIMD architecture would be a GPU, or graphics processing unit, which we're going to talk more about later. There is also MISD, which is multiple instructions, single data, where you can execute different instructions on the same piece of data. That's pretty uncommon. But the most common type of architecture used in HPC architectures today are multiple instruction, multiple data. So you have multiple processors executing different instructions on different data at the same time. And then we can further distinguish between different architectures in terms of how they allocate memory. So a multiprocessor system is a shared memory system where all the processors share a single memory space. That can lead to some problems if different processors are trying to use the same data at the same time. But then you can have a multi-computer system, which is a distributed memory system in which each processor has its own memory. But that requires some pretty sophisticated communication management for all of the computers in the cluster to pass data efficiently. Yeah, so like I mentioned, a graphics processing unit is an example of SIMD. And we're going to talk a lot about GPUs later on, but basically the GPU was designed for computer graphics, which is an inherently parallel task. And people realized that rather than just computer graphics, they could be taken advantage of for kind of general purpose parallel workloads. So yeah, we'll be hearing a lot more about GPUs later on. Okay, so in the early days of HPC, a supercomputer was like a single monolithic machine with custom vector processors. But in modern day HPC, we typically talk about clusters of individual computers, which are called nodes and are connected in a high bandwidth network. So the early clusters were just built from networking a bunch of single core SISD machines. But these days, modern HPC clusters are networked MIMD systems. So yeah, a node is a single computer in the cluster. It has its own CPU, RAM, and storage and accelerators like GPUs typically. And then you have a workload manager that is like the boss of the cluster. It allocates the resources, handles the job queue, and decides when and where the jobs run. So when you submit a job to the HPC cluster, you submit it to the scheduler, and then the scheduler decides what resources to allocate for that job. And an example of a workload manager is Slurm, and that's going to be, I think, what we use in the majority of these lessons. Okay, so to understand the way some trade-offs between different types of network architectures for HPC clusters, we can look at the topology, which is how the nodes are actually organized in a network. So the most common topology for HPC clusters are meshes, and this is where the nodes are arranged in a 2- or 3-dimensional grid, and each node is just connected to its nearest neighbors. So this is an example of a 2-dimensional, 3-dimensional, 2-dimensional and 3-dimensional meshes, and then a 2-dimensional torus where the edges wrap around to connect the node to the node on the other side. There are other HPC network topologies that are less commonly used, but there's a huge
I think Riley.
but I think, yeah.
Riley, sorry, you froze like half a minute ago.
Oh, am I out of time?
No, you just froze like half a minute ago. So we were listening about topologies, and then yeah, something broke.
Oh, I'm sorry about, yeah, EduRoam here at UD is a little unstable, it looks like.
Yeah,
am I
I
coming
can
through clear
imagine.
now?
Yes, we can hear you now. So just like the last minute, literally.
Okay. Sorry about that. So I think I was talking about the different types of topologies, the 2-dimensional, 3-dimensional meshes, and the 2D torus. So these are the most common topologies that you see in an HPC cluster. I mentioned that there are some other less common topologies like ring, star, hypercube, tree that are less commonly connected. And I see there's a question in chat, which is that when we ask for 3 nodes of a cluster, does the queue manager always assign nearest neighbor connected nodes in this mesh structure for any number of nodes? Yeah, I think so. I'm not sure I totally understand the question. Is it? Yeah, Alex.
Yeah, I suppose the question is, I mean, the person who asked may correct me. The question is whether the job manager by default assigns the physically closest nodes, the ones that are have the shortest connection between the node that assigns the job. Okay, so I think that Tomislav and Gordon will answer more elaborately on this, but no, by default, the job manager will assign the node that has the lesser load currently, and this is not necessarily the nodes that are closest to the node which executes the job allocation. In addition, the node that actually executes the job allocation is not traditionally the node that runs computations. So in these cases, we'll probably have a node that is kind of in a hierarchical place than the computational nodes, and that is connected to all the rest of the nodes. But I think that Gordon and Tomislav can answer more detail about how this works. Maybe later Gordon will talk about it a little bit more.
Yeah, I think this will probably come up again. So
Yeah. I'm not into the technical details of the HPC, but I know that you can in fact reserve a particular node when you do the computation, so you can choose the node that you want.
and I think in some in some topologies, like different nodes have different amounts of bandwidth. So one example that we didn't show here is the tree network, which is a hierarchical topology where you have like the higher bandwidth nodes kind of at the top layer of the hierarchy, and then the more specific compute nodes are later down. So when jobs are getting allocated to the lower level compute nodes, it's easier for them for the data to pass through the high bandwidth nodes at the top. So another thing that we ought to mention is the distinction between like the front end and back end of an HPC cluster. So the front end is like the user facing component that when you log into the HPC, this is the part that you're going to interact with. And then you have the back end, which is where all of the computational tasks take place. So all of this network topology that we've been discussing here, this is all this is taking place on the back end. But when users connect to the cluster, they interact with what's called a login node. And the login node is where you can submit jobs to the compute nodes via a workload manager like Slurm. So like in this diagram here, the user can SSH into the login node, submit jobs to the queue, and then the workload manager sends those jobs to the compute node. So you're never interacting directly with the compute nodes. Another pretty important warning here is to never run like heavy computations on the login node. So you always are submitting jobs to the scheduler that then passes those to the compute nodes in the back end. So the login node is a place where you can compile some very like resource light code or manage files and submit jobs. But that's not, you don't want to run any kind of heavy computation on the login node because that will slow it down for all the other users as well. So this is why we submit jobs to the scheduler. Okay, and then in terms of file systems, HPC clusters typically provide multiple different storage locations. And this is something that new users have to kind of figure out which storage system to use. So every user gets allocated a home directory, which is personal storage for that user, usually with only limited capacity, but it's a good place to store some scripts, configuration files, and very small data sets. And then for active jobs, you can use a scratch space, which is temporary high capacity storage. But this is not this storage space is not backed up, and it's usually cleared after the job is complete. So this is for jobs that require a lot of storage during execution, data sets that are not like large data sets that aren't needed permanently, or jobs that need high performance storage than your home directory. But you don't want to have anything saved to your scratch space that you need long term. And then often like research groups that are using a cluster use a shared storage space. So this is storage that's allocated and accessible to multiple different users, and is used like as a shared working directory, and is backed up for long-term data storage. So these are the most common types of file systems, but large HPC facilities can often have more complex storage organization. There can be project and archive storages that store large volumes of data that aren't often accessed. And you can have, there's a slow but also cheap and reliable storage types called magnetic tape libraries that are used to store archival data releases of astronomical surveys, which is pretty relevant to LSST, which is going to have a pretty significant data storage task. And so that the storage is going to be implemented in a different way between different facilities. So it's important to read the documentation for whichever HPC cluster you're using to understand how that storage is allocated. Okay, so I'll wrap up with a couple key points here. So communication between different computer components, depends on what kind of computer architecture you're using, and different computer architectures and network topologies can have trade-offs in terms of latency and bottlenecking, and different, efficiency can differ between different architectures, but there's trade-offs where one architecture or topology might be more suitable for a particular task than another one. And modern supercomputers are essentially just a bunch of regular computers networked together, but the difference is how many CPUs, GPUs, memory units, the RAM accessible to those, the size of the RAM stored in those GPUs, and the clock speed of the CPUs, and also how they're connected to each other. And data storage organization varies from one HPC facility to another. So, it's always good to know the documentation on whatever cluster you're working on. And again, a reminder that login nodes are not for very computationally intensive tasks, because all the users of the cluster share that login node. So you don't want to crash the login node for all the other users. Okay, I think I will wrap up there and pass it to the next instructor.
Thank you, Riley. That would be me. And yes, hello everyone once again. I will talk to you a little bit about which kind of HPC facilities or adjacent facilities are available to the LSST users. And let me share my screen quickly. Hopefully you can see this. Yes, so once again, a little bit of an intro into how it is organized within LSST. So generally speaking, for like astronomical community, we have many different types of high performance computing facilities, or just something that is relatively powerful, more powerful than our personal computers. So one thing that is commonly available for many people in academia is institutional clusters, which can be as small as just several computers connected together to which you log in with SSH and which do not have any job manager software that will automatically assign your code to the closest available CPU, for which you have to do everything manually, install your own software, manage your own environment, and so on and so forth. And while it is a simple option, it is often quite a good option for several reasons about which we will talk in a second. So if you are in some astronomical institute or university, it is always a good idea to ask around whether you have something like this. Asking around is a mandatory step because often these facilities aren't broadly advertised. So you have it, but there is no documentation. And you have to essentially ask people who do this how to use this kind of thing. Another possibility is larger supercomputers. Often it is like national level supercomputers that allocate a lot of time to the academic research. Sometimes these facilities are joined with some weather prediction projects or something like that. Getting access to this kind of supercomputers is more complicated, but then you have better management. Then you have an easier life because usually quite a lot of software is already installed, so you don't have to figure out how to essentially run some Conda environment in this setting. And occasionally, depending on your funding, you may have a possibility to get cloud HPC resources, for example, from Google or AWS. This is once again, this solution has a benefit of having a lot of things predefined and set up quite smoothly because these kind of services are broadly used not just by academic users, but also by different private companies and so on and so forth. So it usually has a better, smoother management than something that we are trying to scramble with our own workforces. But a serious issue is that you have to transfer your data to these kind of facilities, and it is not always trivial. Why? Because if you have a multi-terabyte data set, then first you will have to pay for storage additionally to run some cloud HPC. And second, it will take a long time to transfer this data into the cloud, or often it is just unfeasible because bandwidth is one of the most important bottlenecks in any kind of high-performance computing. So it is a bottleneck within the clusters when you have to pass the large chunks of data between different nodes. And it is a serious bottleneck when you have to pass the data to the HPC facility. And this consideration is one of the reasons why LSST community came up with IDACs, which are independent data access centers. So the idea is, so this is part of a larger program called in-kind contributions. Essentially, different countries are providing work hours of their researchers or computational resources or hours of observational times on some other observatories in order to get data rights for the LSST data releases. So data releases of LSST are going to become public in 2 years after they are released. But before that, some people have access to it if they are data right holders. So if your country is part of this in-kind contribution program, and if you personally are related to some of such programs, then you have data rights. And there are, I think, either 13 or 14 facilities that are providing their computational and data storage resources in order to get these data rights for the international researchers. Most of these facilities have as their primary function to provide data access because, see above, transferring large volumes of data is a huge problem. It is unrealistic to expect that Ruby Data Science platform will be providing everyone in the astronomical community with the possibility of download petabytes of the data sets. So these data are distributed across the globe, and these IDACs are providing access to a smaller parts of the community. quite often without any discrimination regarding whether the researchers from the country in which this IDAC is located or they are located somewhere else. This is up for them to decide, but most of these IDACs are providing the access to everyone who has data rights. Now, a lot of these IDACs are not suitable for running high-performance computing, but some of them do. And we will have a look quickly into a few of them with the biggest opportunities for this. The list is not exclusive. So here is the link to the table in the materials, where you can get a quick look at the full list of these IDACs, at what data they are going to store, and what kind of resources in terms of storage and CPU they are going to have. So if you look at these data products, which will be stored on these computers, on these supercomputers, you can notice that a lot of them will store only object table catalogs, so not even the tables like source tables. If you are familiar with the LSST schemas, then you will recognize these names. So essentially, a lot of them will store only information on the object detected, but not the epoch observations information. And only a few of them will store any images. And essentially, I think that only one of them, only United Kingdom data access point will have, and this is editable table, fantastic, will have the possibility to serve visit images. So if you are doing some kind of, I don't know, science that analyzes faint structures on epoch images, not on deep cards, but on epoch images. So for example, you are studying, I don't know, the expansion of the some shells after supernova explosion, for example. I mean, it's a little bit fantastic example, but still. Then you are in trouble. Then you will have to go either to United Kingdom IDAC or you have to do this on Rubin Science platform. But this is pretty narrow case. So other science cases usually are okay with doing only these tables. So the IDACs that have some HPC capabilities. Poland IDAC will have some few dozens of petabyte permanent storage, about 6,000 of CPU cores, and maybe some GPUs, which is currently like a work in progress of securing these resources for the IDAC. And it will provide the access to catalog data to all data holders, data right holders. Via something that strongly resembles Rubin Science platform. We are multi-purpose notebook platform, and via the possibility there will be a possibility to log in via SSH and run HPC jobs via Slurm job manager, about which we will talk further. So essentially, there will be a possibility not only run your computation in Jupyter nodes with limited amount of resources, but also to request a lot of these CPU cores and RAM and maybe GPUs. This project is in testing stage, and it is expected that it will be fully available maybe in the next couple of months. So I would say that we are going to expect, we are going to have more news during LSST at Europe time. Brazilian IDAC is based on the Linea platform, which exists for a long time and serves multiple data sets such as DSS and DES. And it will also host LSST table data. It has about 1 petabyte of user-provided storage and about 500 CPU cores, no GPUs. And normally it allocates only limited amount of resources per user because, once again, it is a science platform that relies on Jupyter Notebooks development. So it is not a fully HPC facility. However, upon agreement, it is possible to get access to HPC-like mode of execution code. So if you are, especially if you are part of the Brazilian community, or if you have some data science case that relies on having both LSST and, for example, SDSS or DES data, this facility may be your good choice for you. Canadian IDAC, similarly to Linea, is a long-existing project that serves mostly astronomers from Canada, but also a lot of international astronomers use it. And it stores a lot of survey data, including GVST, Canada, France, Hawaii Telescope, Hubble, Gemini, and so on and so forth. So this is like only the loudest names, but actually the list of the datasets stored is quite large. They also have quite a lot of resources, about 3,000 of CPUs, but no GPUs currently. And they can provide you with a little bit more resources for your Jupyter notebook development. So if maximum configuration on RSP is like 4 CPUs and I don't actually remember, maybe 16 gigabytes of RAM. Then in case of Canadian IDAC, you can have up to 16 CPUs and 192 of RAM. So it is an intermediate case between using RSP for some relatively quick and lightweight analysis and going for a bigger scale IDAC with HPC capabilities like Poland one. Also, there is a possibility to ask for more resources if you execute your jobs from the terminal. But for this, you have to get a special registration. So it's not something that you can do by just logging in and running your jobs. This platform has been running for a long time. It is well developed. It also provides you out-of-the-box environment that are specific to the survey with which you are working. And such an environment is going to be prepared for LSST as well. So, for example, if you need to run some of the LSST science pipelines on some custom settings, then Canadian IDAC is probably going to be a good choice for you. Argentina IDAC is being in development, and there were a lot of setbacks regarding securing the funds and purchasing the components, but they had a breakthrough recently. They managed to finalize the funding agreements and bought the necessary CPUs and NVIDIAs. And it is especially important to notice that this is one of the few IDACs that has GPUs available. Although it is planned to serve primarily Argentina Astronomical Society, it may be open to the international data right holders upon agreement. So when it is active, probably in the beginning of 2026, it is a good IDAC to have a look at if you have some machine learning oriented science cases. And it is going to be mostly using SSH access. So no Jupyter notebook development. Finally, UK data facility, which is essentially the only one full IDAC that will store essentially the full volume of the LSST data releases, not only object tables, not only epoch tables, but also images. So if you have something for which you need to do image analysis, this is the place you go, apart from RSP, obviously. However, the number of the amount of resources allocated per user is similar to RSP, so it is not actually an HPC facility. It is indeed a data access point. So about 4 CPUs and 16 gigabytes of RAM allocated is what you can account, and anything more, it has to be set up additionally with some other UK-based facilities which can quickly communicate with this IDAC. So this is something to go if you need to do image analysis, somewhere to go if you need to do image analysis. And finally, Croatian Scientific Processing Center, essentially supercomputer Bura, about which Gordon will tell you a bit more in a few minutes. But just briefly, this is one of the, once again, few facilities in this list that have their primary goal, not data access point, not as data access point, but as computational facility. It has on board both CPUs and GPU nodes, so you can use different types, so you can use it for different science cases. And the access is provided mainly through SSH or through web-based access point, but it does not have Jupyter notebook development environment. So what do you do when you need to decide which HPC facility is for you? Obviously, it depends on your science cases, but several important things to consider is what kind of calculations you are doing. If you are doing something that relies on machine learning packages, so PyTorch, TensorFlow, something like this, you are likely, not likely, but you are definitely going to need GPUs, and that narrows down the list of items significantly. However, as I mentioned before, sometimes small-scale institutional clusters are a good choice. And this is actually one of the opportunities, one of the cases in which institutional clusters are sometimes better because they traditionally serve different teams, including some of the teams that are doing very popular topics related to machine learning. So these clusters in the last few years usually are obtaining GPUs. So have a look at your local working environment. Maybe you will find something suitable there. However, if you need to do massive data analysis, then you have to go to IDAX because transferring more than several dozens of gigabytes of data from one place to another is a huge problem. You are unlikely to be able to do this. So when you have some massively computationally expensive project, it is pretty normal to split it in chunks to do the data analysis, data retrieval part on the facility where the data is stored, reduce the volume of the data that you will be doing the further analysis, and then transfer it to a facility that has either GPUs or a lot of CPUs to do your work. And another thing to consider is what is the code, what are the dependencies that your software uses. So one thing, if your code is pure C, C++, C#, or even Python, okay, those things are usually installed on many computers. So maybe with some tweaking, maybe with some arguing with the administrator, with the admins of this facility, you will probably make it running smoothly. But if you have some dependencies that are more specific, for example, you can think about Gadget, which is a code that was developed specifically for cosmological simulations. So if you think about simulations like Illustris or Illustris TNG, this is the project for which this code was developed. So if you have some not widely used libraries, then it may be problematic to install them on HPC, especially if you don't have the direct access to the admins. So this is another thing to consider. And also the trick is that if on a smaller clusters, like institutional clusters, sometimes you can run your software in containers. So you can pack the environment and you can pack all the dependencies inside, and you can just put it on the node that you need and you can execute it on this node. Then on larger supercomputers and clusters, it is often impossible due to security reasons. So yes, depending on whether you need to execute some custom code, some specific dependencies, it can be more complicated to do this on a larger scale, on the large scale HPC facility. More information on this you can find in this table that is listed in the materials, and also usually any big LSST conference has a separate session on IDAX, so it is a good place to go if you want to stay tuned. But for now, we are going to switch to the HPC Bura, which is a Croatian in-kind contribution, one of two Croatian in-kind contributions, and which team kindly agreed to walk us through to how HPC facility is organized and how to work with these kind of supercomputers. So I will leave floor to Gordon, and I will stop sharing my screen. And this is it from my side. Gordon, please.
Okay, let me share my screen and my camera. I hope that you can see me and hear me well.
Yep.
Okay. Just a second to set up my screen. Can you hear me?
Yeah, I can hear
Yes,
you,
very
Gordon.
well.
I have some issue with Zoom, obviously.
No, Zoom appears to be fine. We don't see you sharing a screen.
Okay, I have a problem sharing the screen.
Okay, I see.
Okay, I will share full screen.
Yes,
Well,
we can see it.
First couple of words how to access Bura. Since every HPC system has its own, let's say, unique features, I will tell you a little bit how to work, how to access and work on Bura. Well, first, let me introduce myself. I'm Gordon Janes. This is my email. If you have any questions later, feel free to contact me. Also, this email address you will have in material. I will skip this slides, or these two slides from my last presentation, but I intentionally didn't delete them for this presentation. It says where supercomputer are used in a science or everyday life. But let me say a couple of words how supercomputers are important. There is every 6 months there is update of top 500 list. It's a list of top 500 most powerful computers, and twice a year there is a supercomputer conference. Once once per year, usually in Las Vegas, and usually in Hamburg, and every 6 months this list is updated. In the last couple of maybe 10 years that I'm following this list, probably if you are below 400 listed on a below 400 position, you will probably not be on that list within 6 months. That means how widely and intensely are supercomputers used. And now in the last couple of years, artificial intelligence bring a whole new dimension to do high performance computing. But let's focus on Bura. This is actual picture of Bura. It was taken a couple of days before started to work. But first, just a couple of words about when it makes sense to run your software on your code on a supercomputer. Since many users, especially those who are not very experienced, think that every code will run better, faster on a supercomputer. But sadly, this is not true. But usually is. But when it makes sense, when the problem is huge in size, you will use a supercomputer. For a small size problem, there's no sense to run these calculations on your personal computer, since you will probably spend more time setting environment, uploading, downloading data, etc. Simply makes no sense. There's also a case when you have a calculation that lasts for an hour, more than a couple of hours, usually days, weeks, or sometimes years. Then it makes sense to run this code on a supercomputer. And the most reason why most users run code on a supercomputer is needs for specialized hardware. That's usually a need for many CPU or GPU. Well, when your software is capable to use multiple cores at the same time, or multiple GPU accelerators. This is very important since especially unexperienced user they put single thread code on a supercomputer and request 20 cores. That doesn't make sense within a supercomputer world, with supercomputer environment, since this code will not use 20 cores. You are just reserving space for a 20 cores, but actually you are using just one. And there's also one reason when to use a supercomputer is when you have too many jobs for a personal computer. This is our department of physics. Sometimes has thousands of small jobs that run for a couple of hours, but altogether they last for a couple of weeks sometimes. Then it also makes sense to use a supercomputer. Am I talking too fast? I hope not. I'm talking
I
fast.
think so far so good.
Since I have quite a lot of slides and I want to tell you how to use supercomputer as efficient as you can. How to access Bura? Well, we are directly connected to the CARNET. CARNET is national internet provider, academical internet provider, and we are directly connected to the backbone. We are not using university network. We are directly connected to the national internet backbone. And we have a 10 giga upload and download link. And when it comes to the redundancy, we have 2 access points. Well, one is right now used only for special purposes, but this is not what I'm talking about you today. So let's keep, this is actually live map. I take a look where are people from connecting to the supercomputer. This is live picture, maybe 1 minute old. But let's speak. This is the address. Are you all, did you all get your username and password? Any user without username and password, feel free to contact me. After this, I will give you username or Alex will give you username and password. Actually, for connecting to the Bura, we are using virtual private networking. The reason is security. There are 2 reasons. Main is obviously security. The other is we are providing some other services than the classical computing calculations, like collocation of servers, license servers, etc. So for these features, we need a VPN tunnel. So to access Bura, you have to use special software or simple ways to use just to access Bura using your web browser. As I mentioned, these are 2 reasons why we are using VPN. This is the address. It's Bura. It's the name of the wind that's quite strong here in Rijeka region, this part of Croatia. UNIRI, it's University of Rijeka, and AGR, it's a national code for internet code. This is a second auxiliary entry point. Well, you can access Bura via web browser. Actually, when I set up this a couple of 7 or 8 years ago, it was auxiliary just for a couple of users. But now, actually, maybe half of users use web browsers to work on supercomputer Bura. I'm surprised since the classic SSH connection will provide you more comfort and easier file transfer, etc. But I don't know. the actual reason, but most of the users use the web browser. You're free. When you log in, you'll see something like this. This left two buttons that says SSH, Bura 2 and 3. Bura 2 and 3 are our login nodes. And you can use the two FTP servers to transfer files. Yes, you can also transfer files with your web browser, not only work with the SSH. And that is actually all that you need when you connect to the supercomputer. You need the SSH connection and the file transfer to download and upload your files. Actually, I had I was noticed by a few users that they were not able to use access via web browser, but later we figured out that they are using some old web browsers that do not support HTML5. So please check out your web browser uses HTML file, and 99% it will use, and you will have no problems with the access. As I mentioned earlier, you can also transfer files via web browser, and there are two servers. They are sharing the same storages. They are just here for redundancy. There's any difference when it comes to the install software or licenses or limitations. Bura 2 and 3, they are here just for redundancy. There is no better performance on Bura 3 or Bura 2. So use them randomly. This is how the screen for a file transfer looks like. So that means that you can do everything with the web browser, but to have a full comfort to work with the supercomputer Bura, my advice is use VPN software. We are recommending FortiClient. It's a product of Fortinet. Company called Fortinet. It has many versions. It supported all major operating systems like Windows. I tested this software on Windows HP 7, Vista, Windows 10 and 11, Linux. Android is also supported. Yes, you can install this software on your cellular phone and access Bura also. You can obviously from a Mac world, from a Mac, from Apple computers, you can also access using FortiClient. Also for a Chromebook operating system, it's not so widely used, but it's also supported. There are some issues with some exotic versions of Linux, but just a couple of cases were reported to me, but all of them were successfully later solved when it comes to the VPN connection using Linux. And you are not restricted to the Forti-client. There are also some other software that support VPN. If you have this software already installed on your computer, you can try it. Bura, probably it will work without any problem. There are actually, I have to mention, there are two versions of Forti-client. One is with the integrated security like antiviruses, etc. It's you have to pay for this software, but there is also a version, free version, Forti-client VPN without any restrictions. You don't have to pay for it. And you can find it on a site Fortinet on the Forti-client.com. when you are accessing Bura, you are creating through the internet. You are creating actual VPN tunnel. That means that that adds another level of security in your connection. But I have to also mention on most supercomputers that you are going to access, you can access only login nodes. You actually are not able or permitted to log in on or directly to the computational nodes. You log in just to login server, prepare your job, upload, download data, and submit your jobs to the computational part of a supercomputer. When it comes, when you install VPN software, obviously you need additional software for as an SSH client. PuTTY is one of the oldest, most famous SSH client software. And there are also many variations of PuTTY on the market, like Super PuTTY, PuTTY Tray, Kitty, etc. I prefer a Bitwise SSH client. And there is also on PuTTY homepage, it's since I think for the last couple of years, it stopped development of PuTTY, and they are also recommending this SSH client, Bitwise SSH client. It's a very simple to use software, but on the other hand, there are many features that you can set up according to your needs or wishes. And it also enables quite simple file transfer, like a Windows Explorer, drag and drop feature. There are also many free software I mentioned here on this slide, couple of them like MOBA, terminals, etc. They are all powerful. Actually, you probably won't use you'll probably use just a small part of feature that they offer. But there are also, why I mentioned this is there are many products that you have to pay for. Please don't do that since you are wasting your money. There are a lot of free software right now in the market. When you log in on your on the Bura, this is how it looks like. You can have a multiple windows or slides of you can have multiple connections within the same browser to the Bura, so you can work one thing and I don't know, put some code, upload file, etc. in one, and in the other window you can check how your job are running or etc. There is no limitation when it comes to the number of windows that you can open to the Bura. This right part of a slide show when it comes how it looks like when you are connected using Bitwise SSH client. And this is all from me now. Just a couple of words, since I have a lot of material later to do, so let's skip to another presentation.
Thank you, Gordon. Apologies, I was looking for the microphone button. So, any questions at the moment?
We can speed up. They can also send me questions via Zoom, textual questions, or via email.
Excellent, thank you. I have a question. How about we do a small break right now, because I actually forgot to put breaks in the schedule. And then we will resume with the command line episode. And then we will continue with the Bura setup, and probably we will do another break somewhere midway, but probably after Bura setup, and then we will do the Slurm session. How does it sound?
Great, since I have more than 80 slides.
Oh my God. Okay. So let's say right now it is 18:17 where I am. So let's meet again at 1/2 whatever hour it is in your time zone. So in 12 minutes. Is it okay?
Yep.
Okay. Then in 12 minutes, we are going to be back.
If there are any questions, you can ask me now, or so we don't waste time.
Hi, Gordon. Maybe you know the answer from a previous session. There was if you look at the chat from Navin, there was a question about the nodes and interconnection. It's not connected with Bura, but maybe you know this is more technical question. I mean, I can read it. When we ask for 3 nodes of a cluster, does the queue manager always assign nearest neighbor connected nodes in the structure, or you just assign random nodes around?
By default, Slurm is not aware of interconnection topology. But yes, there can be some priorities. There can be configured some priorities in your Slurm script. Usually, we are actually in the Bura we are using FAT3 topology. I will have to share a screen for that. What FAT3 topology is.
Hi, Gordon.
Right. Just a second. How to show? Can you see what I'm sharing right now? This is the
Yes.
topology.
Yes.
Yes.
I did some testing. First, I have to say we are using InfiniBand connection. Hardware is based on Bura Bullix, Atos, Bull Atos hardware, and that means that there are 18 nodes, computational nodes with the same chassis that are sharing same first level network switch, something like that. I did some testing, but there was not significant improvements or slow learning code on this hardware. On the other hardware, I I don't know actually what will be the performance. You have to test it. But in a Slurm, you can test it since you can specify nodes on which your calculation will be running.
Yeah, thanks, Gordon. Thanks a lot.
Last year I did, or 2 years ago, I did some extensive research on Gromax. It's used for computational chemistry, and I was testing number of nodes, number of cores per task, etc. And I will show you. I'll tell later a couple of words about it. But here on Bura, I didn't see any improvement in performance, so I don't see the point specifying the nodes for your job. But yes, you can do it in Slurm. One hint is if you are trying to do this, use nodes. Usually nodes have their number, let's say Bura from 100 to Bura 500. Use nodes that are quite close to the with the numbers, or they are neighboring nodes.
So this is 6:30 where I am, or 5:30 whatever time where you are. And the next episode is on command line, which is the most important tool when you are doing any kind of remote computations. And I think that for this episode, Angelika is going to walk us through the main commands and through some exercises. Is this correct?
Hello, yes, just to try to share the screen.
Yeah, go on.
Am I sharing?
So you are broadcasting. Yes, so we are seeing exactly what we see on your screen. And currently I see myself, which is weird.
Okay, okay. Just a moment, please. Okay, I will switch another from my computer. I'm sorry.
Okay, no problem. Go on.
I'm sorry for this. And I will go to my computer.
Okay, we see the screen, but we cannot hear you.
Okay, apologies. I apologize. Okay, this is the second episode. My name is Angelika Kovacevic, and I am a in-kind contribution lead to the LSST. This episode is collated by many wonderful colleagues, presumably Azali Bostrom, Alex Razim, and Meet Vyas, and also includes material that is kindly supported by Meet, Marcus, and Riley. So you will see all of them, and mostly and importantly, we are thankful to Mr. Gordon, Janusz, and Tomislav for providing initial material for this episode. So this is oriented, as we have already seen, some architecture archetypes of the HPC, and we as the in-kind contribution team had a wonderful connection and interaction with Professor Tomislav and Mr. Gordon Janusz running some of our codes, and it is my honor that we can share this intro in this lecture. As Alex already told us, the main idea for this lecture is actually that it is the hands-on, and it is related to the command line interface. And we know that command line interface looks a little bit old-fashioned, but that is only because it is descendant of the way of interaction, as we already heard from Riley, with previous types of the computers. And for example, in 1950s, 1960s, computers were mostly on punch cards or some magnetic tapes, and in order to execute even simple for loops or whatever you may be waiting for whole day or days. But command line was a really exciting development in interaction of the human with the computer, because it allowed a live interaction with the computer and execution of the command. So you are typing in and immediately you can see the results. So before 1970s, it was not possible, but in 1970s, it was invented by Unix, and after that, it became like the common denominator for interaction with the computer. Later on, we have development of the graphic unit interfaces, which are more democratic way of interaction with computer. But command line was actually something that was firstly developed, and it is all the time, and it allowed actually that we have collating of many such simple commands into scripts that can be actually executed through the shells on the system. And that was wow in 1970s, 1980s. And Presama, and we believe that it will be also important for the, not now for the interaction of high performing computing centers, but in the future. Maybe it will have some different form, and we can see some different form already on GitHub when you are deploying your programs, packages in order to be propagated and deployed on the GitHub. You need to collate them, to profile them, and that is one aspect of this. But we believe that in the future we will have more democratic way of interaction with HPC, because now the learning curve for the command line interface may be steep for the beginner, but as much as you are involved with this, it will be much more easier. So of course, development of other ways of AI and combination of the graphic unit and the command line, you can have more control and more finer experience of interaction. And in this lecture, we will have 45 minutes for hands-on. Here is the some general overview of how it looks like, the architecture of our rooms on Bura. And there are actually some space that is reserved for our participation in this workshop. But there are also some really important directories, and we as LSST members and community, we are promoting ethical use of the resources and being careful how we actually access the computing centers. And mostly we will actually have, as you already seen in your shells, we'll have some space dedicated to us where we can make our programs subdirectories. What is important? Important is always to know where you are in, because in the command line, it is actually very easy to make a mistake, specifically typing in. And some people with certain disability, with certain different abilities, maybe it is complicated for them to be perfectly in typing all the time. So because of this, we should be really careful how we fill in the command lines, because even one character may be meaning deleting something that is important. And there is a very first command. Actually, this is the very first introduction to know what is the working directory where we are working now. And if you put in order to see the short list of what is the content of your directory, we can see here some already introduced scripts related to the interaction with Bora that you have in the introductory material shared by Mr. Gordon and Professor Tomislav. And using the listing command, we can see just simple list. But then you can actually see the all items in your current directory, and you can specify the path. And of course, in order to see in the directory the files with different attributes, for example, what is the hidden, you can maybe use this command ls-a in order to see some hidden files among the other files. These hidden files are usually important for the execution of some other programs, and also can specify workflow. For example, for the GitHub, you have some hidden files that you need to create in order to make the workflow of your package deployed on the GitHub. That is the same on the Bora. So actually the hidden files starts with dot and then the name, and seeing them is through this flag. Also, you can add other flags, and you can access all commands through help function like man. And we also have some extras of material where you can find some cheat listings of these commands. But there is some important option of the flag like -f, which actually allow us to identify the types of these files. And of course, it is possible that we collate multiple flags that will actually provide more verbose output than single flag. So I encourage you that you try also this. Importantly, when you are compiling these commands, please be careful not to copy this $, because it is just symbol from the shell. Important, of course, is creating directory, subdirectories, in order that we can work in them, because it will be important later, and also important for your programs, for storage of the data, for storage of the models, invoking them from them. And of course, when making the names, be careful how you are naming the directories, following some conventions, in order that you do not make the spaces between the names, and you can actually collate them through this lower dash line. Then of course, we should change directory. So this part is mostly related to the acrobatic movement across the directories, subdirectories, and knowing the naming of these entities that you are creating on HPC. And importantly is actually to know that meaning to move backward from your present directory is actually to moving up on directory tree. So it is, if we have analogy with the graphical unit, then we always have this arrow pointing on the left that is like the back that we click on in order to go back one step up in hierarchy of the directories. So in that means moving backwards or actually is moving up in the hierarchy of the directory, and you can use actually this cd // command. Importantly, you cannot, for simple moving one step backward, it is not necessary to put the slash, but usually it is important because sometimes we should actually refer to longer path, and then we should have a slash and then the part related to go backward. So you can be aware that putting slash like this here is to be cautious, that you know that maybe sometimes you will need full path in order to go back. So you can execute with or without this for going one step backward, but usually maybe sometimes you need to move 2-3 steps more, and then not to forget about path. And then you have the exercises and solutions of making directories, seeing, printing working directory, making subdirectories, and listing those subdirectories. So, and of course, we are encouraging you to autocomplete with using tab the commands, and that is like I already mentioned in the beginning, very helpful for the people who are specific with typing in capabilities in order to not to make mistakes. So here is this difference between the about going backward in the shell, and once again it is similar with the graphical unit with the arrow pointing on the left, which we all know going back, and the arrow pointing right means going forward. So here, instead of the arrow on the left pointing, we have 2 dots and then slash. And here is the exercise related to this about the motion, movement across the directories and across directories trees. And of course, there is some printing, simple printing on the terminal through echo command. And importantly, we have some file manipulations that are important for reproducibility. And then we have maybe some many tasks like batches of the data that should be executed. And of course, these commands can help us with efficiency, as you will see through this session with Meet and Azali and Marcus. And when you are opening, in order to open your text files, actually scripts as text files in order to write in, you can use maybe different commands. And importantly, command line interfaces on different systems can be different, a little bit different. But here we provided examples with nano command. And then when you type in nano, and then the name of your script, which is consisting of the command lines that can be executed at once, you can see at the bottom these 4 possibilities. And importantly, never forget if you may change something to save it with Ctrl+O, exit, cut line, or paste line. So that is something important. And you can see the output for your simple shell example shell that you already made. And then you can run your shell script with the source command, and then you will see the output of this. And then you will see in some cases, maybe you need that you put a sleep for a few seconds to stop running the command shell. And for that, we provided here the exercise, interesting exercise, thankfully to Azali and Alex, about, you know, how to actually to add new line in the nano shell, and then to put into shell, and then to put the script into the shell example script, and then to execute it. Of course, we can move our shell, scripts across the directories with simple command here, and we can also rename our shells, our scripts, sorry, with the command move. And we can actually copy the files with the cp command, but instead of moving, we can, or renaming, as you can see here, we can actually use the copy command, and we will have duplicated file. Of course, importantly, that we know where, before doing copying or deleting, where we are doing this, and then we can, for example, copy our file that is located in the code subdirectory into other file that is called --3 share file. And of course, importantly, we have deleting command, and deleting files on command line interface is not so easy, in sense that many things can be destroyed unapologetically, to say. So please be careful how to use remove command for deleting files. It is possible to do in recursion deleting files and directories. So we didn't put here this command, and I used some of them, you know, but I do not recommend. And here is some safe way how to use remove command. On the same example in the subdirectory code, where we have 3 files, and then how we can remove safely with iflag, which double check with us, is this the file that we want to remove. And of course, we can have some special exercises, little exercises related to previous comments. And here is important part related to the file permissions. When we list with the command ls list dash all what we see L, we can see actually this first 10 letter, to say characters, And the first character here means that it is something ordinary file. But then we can see there maybe letter D, which means directory or something else. And also the next three spaces can be related either to read, write, or execute. And that is related to the owner of this account. And then we have the next three position related to the group. Maybe we are associated with some larger group, like in these exercises, that is education, students, and we are called edu, and then number. And then we have the others. So that is, and it is important that we can change the permissions of reading, writing, or executing. And also you can see the size of the file, and then when it is modified, and of course the name. So it is important to whom we will allow to see, to interact with our files, and that is something similar what we have in graphic unit interfaces, giving permissions that somebody sees our presentation or the Google document, but here it is more manually. And you can execute the name, and you will see that you are in the group. Which group? edu02, for example. I am in edu30. And then with change mode, we can actually change the permission, what somebody can do with our file. And changing of the permission is like subtraction, minus sign, or addition, like plus. And you will have this exercise in this prompt here. So you will list your already made file helloworld.sh, and then you will try to change the mode so that actually to give everyone else ability to execute that file. So actually we have that all users means owner plus group plus everyone else. So all users means O plus G plus owner plus group plus everyone else. So the changing, what is possible to do, you can see in this exercise, and then some little bit advanced exercise to modify permissions to remove group's ability to read the file, and of course to double check about that permission, and then to add the permission back. So that is here importantly adding permission by to add here change mode for the owner to execute hello world. Then after execution we will have this. Sorry, here is for the everyone else. Okay, apologies. And here is what we already said about the ethical usage of the HPC, to be careful about the ethics, and whatever we are doing, it should be in academic way and supporting collaboration. And here is the section related to the disk. What we have on the disk, how much of the space we are using, and that is through, we will see 2 comments here, maybe there are 3 comments that you already use, and the first comment is du, -h directory, where you can actually see the format of the in the human form, in the human readable format, what we have in our directories and how much of the space is dedicated to each of the subdirectories or directories. And of course, if we for interruption of the execution of any command line, we can use Control-C for interrupting. The other command is stop, and that command is mostly used. It is some kind of linear command presenting the in the simpler way the directories, the amount of the disk usage, and then you will have some other how to say data related to or parameters related to this. But there is also the third command, htop, which is more human readable in sense that you will see all users who are now present, how much of the disk space they are using, what processes are idle, what are active, what are actually sleeping, and that is the htop. Importantly, you can interact with the lower menu on the htop by clicking on the, for example, maybe you will see F10 exit. You can click on this and then you will exit that htop command. So top is something which is more, which is quick interaction to see what is happening and what process is stopped or idle or executing, but you will not see what is happening at present time all around you. And then maybe you will need for your execution of your programs or models to store the data on some specific space, or to store the model. Maybe you are training a machine learning model, and then you should save your checkpoints of the model, and then you can decide to save this on some specific locations. And for this, we are using the environmental variables, but also the most important environmental variable is path, that is general variable, environmental variable, which we can see, which we can actually print by echo path, $path. We already see, we have seen the echo command, and then you will get something that, like this, how actually is your directory where you are now present related to the more general directories. And of course, in order maybe that you want for your machine learning program to have the data on certain subdirectory, then you will define in the command line the environmental variable data directory. You already know this from the Jupyter notebooks and from GitHubs. And then you can see actually how it looks like here. But please be careful that your program actually, or in command line before, in order to access that data, that you make that directory and then to store their results of your program. Otherwise, the variable will be just dummy variable without and that is explained here. So be careful, just exporting and creating environmental variable doesn't mean that you created directory. And in order if we make mistakes and if we override the path of our working directories with something that is maybe dummy, eco variable, or dummy variable, environmental variable, then we can actually simply recover our path through this command. And here is finally what we have related to the question by our colleague, how to handle and acrobatic handling of the files from the local computer up to HPC, or from the HPC to the computer. And that is actually done through secure copy. In order that you secure copy in this exercise, firstly, do not disconnect a VPN connection, but disconnect your terminal. You can open the second terminal which is not connected to Bura, and then copy this command to your to that terminal that is not connected through FTP with Bura. But please be careful to put your group name. Not this is just example. For example, my connection will be edu30, and then it will go like this. And that command will actually download the file from HPC to your own computer. There is also rsync, which actually is something similar what we have on GitHub when we are pushing some files that have differences than the files on the GitHub. We are doing syncing, and this rsync command is really powerful. So it can actually only copy the parts in the directory that are different, that differ from your directory on HPC, but also it can copy the whole directory. So secure copy can only copy files, but rsync can copy whole directories, and not and of course, if you made the difference in your directory on HPC, it will copy only that part, those files in directory that are differ. So it is nothing unusual. You already know this from GitHub. And of course, you can have the file transfer protocol, or SVTP, with the in logging with Bura. And the syntax is already what you know, and you can use for these connections in FTP or SFTP get command. And important things, you can see here important syntax, what you want to copy, and then it is going where to put this. And here is the exercise related to the material kindly provided by Meet. There is some zip file that you can access, and then you can actually try to move this file on your local computer, and then to upload to Bura through SCP command. And some other useful commands importantly, command line interface is non-democratic in sense that it is not so easy, but it is easy through man or how to pronounce man command to see what is what are the possibilities, but there are some extras in our files in these lectures, so you can see how to change owner, how to grab or maybe concatenate many text files, and how to kill processes, and some other system management commands. So that is the section related to command line. And if something I forgot about, I would like to ask other lecturers to help.
I think everything is good, Angelika. Thank you. I think the only thing that I would like to do is to give people about 5 minutes of time to go through the exercises in case someone didn't do it along your explanations. And especially the last exercise with downloading the files for the workshop and SCPing them into the Bura. I think that we will take a few minutes for everyone to finish this. And then if there will be no questions, then we will give the floor back to Gordon for explaining us more about how Bura is organized and how to use Slurm. Does that sound good?
Thank you.
Thank you, Angelika. So let's give like 3 minutes, 5 minutes, and then we will resume. And if you encounter any problem, if you cannot SCP the files to the to Bura, or if you see something that you think is completely different from what is described in the materials, please ping us so that we could troubleshoot it for you. Okay, so hopefully everyone managed to do this. Can I please get a list of thumbs up or raised hands from everyone who finished the exercises, who did the SCP of the files that you downloaded from the Google Drive? Is everyone still doing this exercise, or is everyone just sleeping?
I am in the middle of finding the files and copying them. So I'm sorry.
Okay. Okay. Well, nothing to be sorry about. This is great to have feedback. Okay, let's wait a couple more minutes. And if there is some specific issue, just don't hesitate to unmute and say so. Okay, I see one of the participants managed to finish this exercise. How many other participants have went through the exercises? Raise your hand. Thumbs up. Okay, one. Everyone else is probably still working. Okay, let's add 2. Let's add 5 more minutes. Obviously, we talked through this a bit fast. This is totally fine. Let's take a few more minutes. Antonio, do you have a question, or are you just letting us know that you finished the exercise?
No, I finished the exercise.
Okay, thank you for feedback. Good. Katarina?
I have a question. So
Mhm.
I managed to copy the files, but the connecting to Bura through command line is stalling for me. And it may be connected to the VPN that we also have at work. Should I just try to access it through the web?
First question, are you using a web browser or a command line?
Command line.
Okay.
Just to step in here, but since I'm also working on the same work network, I have to say I've had trouble connecting to the VPN. I'm personally been able to get in using the web system.
Okay, I will do that.
Yeah, I have not managed to connect through the VPN. I don't know why. There's some sort of weird networking issue there.
I have managed to do this last week. I was managed to access it through the SSH through command line, and this week it's just I don't know, like it's been wonky.
Okay, well the web interface for me has been pretty seamless.
Okay, good. But the weird thing is I can use command line to copy the file. So I don't know. I don't know how that works. This is some weird.
Yeah,
I'm sorry, Katrina.
Yes.
For example, my terminal now is frozen.
Okay.
And then you can just disconnect, just kill the terminal, open new terminal, and then try. But do not kill the VPN.
Yeah. No, I will keep the VPN running. I'll just use the web interface to do the command line
You can also try through command line.
Yeah. No, I think we have this VPN at work with Rachel, and it's been known to cause some issues sometimes. Okay.
Okay, so we have a question from Aum. I hope that I pronounced your name correctly. Regarding the using SSH bar through web, put in nano show example SH and so the SH file was opened, but then there was no possibility to exit nano through web. I actually haven't tried this in web interface. Let me try this, and maybe someone who already has experience can tell what is going on there.
Yeah, Alex, I can help with that.
Okay, go on.
So you need to, if you open Nano, you need to do Control plus X to leave instead of just typing X. Yes. Tomislav also pointed out the same thing. Yeah. If the problem still persists, just let me know. We can definitely help you out. If it like still persists, you can also share your screen. That's completely fine.
Thank you, Meet. Thank you, Tomislav. Katarina, did you, it's probably not Katarina, but Katarzyna, I believe, I apologize. Did you manage to solve the issues with Nano and the VPN?
The VPN is up and running. The OpenFort.
Okay.
Oh, yeah, it's running. It's just that when I try to open connect through SSH to Bura, the connection times out. But I don't have this problem through the web interface, so I don't know. Oh, and
So
my
it's
name is
what-
yeah, sorry, go ahead.
So it's essentially, it does not want to connect to Bura through the SSH, right? Because the timeout, so it does not get a response.
Yeah, but I can use SCP through command line. So I don't know.
Okay, it seems like maybe the setup is somehow, but were you able to do it before through SSH, through the terminal?
Yeah, I was able to connect on Friday without any issues. And then like last week in the early part, I couldn't. So I don't know. I suspect that there's some clashing between the
VPNs.
The VPNs, yeah.
Okay, maybe we can troubleshoot it in detail a bit later. So far, I think it's not critical.
No, and I maybe I also will have a little chat with our IT department.
Okay, or maybe even try running it from home and see whether it works to determine whether it's something is the settings or with the VPN.
Yeah. Okay, good. I'll try that.
Yeah, thank you. And did you solve the issue with the Nano?
Yes, I did. Yeah.
Okay, so I hope that most of you have reached some point in the exercises. Since we still have a lot of materials to process, we will pause with this section now. Maybe we can work through it a little bit later. And for now, we will give the spot to Gordon to walk us through the rest of the materials on Bura and Slurm, because there is a lot of stuff to cover and we have like 1 hour and a half left. So Gordon, whenever you're ready, feel free to start.
Well, I'm ready and we can start.
Great.
I will talk fast again.
Please don't.
But there are so many features that I want to talk about.
Talk slower but deeper. It is better for absorption of the information.
Okay, let me share a screen. Well, these are main questions that we will cover in this slide. First, I have to say something about the Bura that I didn't mention in the first part. Actually, Bura doesn't have a limitation when it comes to resources on storage and computational power. But I have to say that doesn't mean that everybody, that this is anarchy, that everybody can run as much as he wants. Actually, you will be with email, we can agree on certain resources then you can use, and please don't use more than we assign to you. Well, why we didn't imply restrictions at the first place? We want to Bura be used as much as possible. That means if you have a need for more resources than you are assigned to, well, you can just contact administrator, that will be me, and we can agree certain amount of resources at a certain time that you can use with as much as you want. Also, when it comes to the storage, there is no restrictions, but when you reach certain limit, certain amount of storage, you will be warned. If you don't remove your data, I will delete it. As simple as that. But for now, for last 10 years, actually this regime on Bura works perfectly. With just a couple of warnings and just once I had to delete some data. Okay, let's go to the next slide. When it comes to resources, there is also one limitation that most of the users are not aware of. At a certain level of resources, especially CPU, speed is not growing linearly. That means if you are using one CPU core for a certain calculation, 2 cores will probably run as much as let's say twice faster. But when at a certain level, I don't know, 100 or 500 engaged cores, probably performance will not go linearly, or usually will go down. This is this simple limitation of networking, of hardware, interconnection, memory, etc. So find out what's the optimal amount of resources for your application. This is a good example for it. I was testing GROMACS. It's a computational chemistry application. I was running it up to 100 nodes. Here is a table only for from 5 to 100 to 80 nodes engaged on a single job, on a single calculation. That means from 250 cores to approximately 4,500 cores. And you can see how much actually configuration and number of engaged nodes can have effect on performance. Greener is better. Red is worst case. As you can see, from 80 hours, 81 hour, what was, I think, yeah, 81 was best, no, 71 was best time that finished the calculation, to up to 1,000 nodes, 1,130 hours. Please, when you are engaging resources, do it properly. Read your application manual. It can significantly improve performance of your application. First topic that I will talk is how to find and use the software in a shared supercomputer. There is also another topic, really, how can I use and install software using apt-get command? How do I manage different versions of the same software? Yes, it is possible to use multiple versions of software on Bura. How can I install Python packages? A couple of words about it. But first, let's talk about how to find software that's already installed on a supercomputer. We are using LMOD environment module system. well, working in a multi-user and multi-application environment is quite challenging, but this is quite good solution for this is LMOD or environment modules. How does it work? Let's say you have application, name it A, that uses Python with the version 3.1. At a certain point, you need a newest version of Python for that application. You want to switch to the newest version? Yes, you can do it without installing anything, with just one command, with just executing one single command. So you can change your environment and switch to the Python version 3.14.7. There can be also, you can switch among applications, also very fast and very simple way. Let's say application A needed Python version 3, but we are switching to the new application. You're working with a new software called B, and this software needs CUDA for any support for MPI. You just load new environment modules, and these two modules will be applied together with the Python, and you can run application B within this environment. Yes, you can easily go back, let's say, switch to the CUDA 9 in a very, very simple way. How to do it? There are 5 simple commands. First one is module available. It can be also used. I will switch to the, just a second. Can you see this?
Yes, we can see it.
Yeah.
There is a first command is module available. Here you will have a list of all software and all versions of that software already installed on the Bura. You have to just put down the command module avail. Avail is short of available. Probably you found some software that you need. How to activate this software? The other command was module load. But before that, just I forgot to mention, when you are searching for a certain software, you can put just a part of a name regardless of case. Let's say I'm searching for GCC compiler, and it will list all the modules that have GCC in its name. If I'm looking for, let's say, root is software. No, already. And you can see a list of all versions that the software that are already installed on a Bura, so you don't have to install it yourself. How to use modules with your module load. Just if I run this command, it will default on this version of on Linux. Default Python is 2.7.5. But if I load I loaded this newest version of Python. I didn't specify which version. It will load me the latest version of Python. When you see the list, it will list you list will show you if there is L at the end, that this module is currently loaded, and D if this is default module. So you don't have to write all this text. You can just write first part before this slash. It will load latest version. This is the usual default version. How does it look like if I put down command Python 3 version? But I can switch to another version of Python. I can switch to, let's say, to this version. It says the following module have been reloaded with the version change. And now if I check version, it will say that I am using this version. With a simple command, you can activate as many modules as you want, but keep in mind that you cannot have two versions of the same software installed and activated in the same time. Obviously, they are in conflict, so they cannot be used at the same time. Well, next command is module list. It will list all the modules that are currently active, that I already loaded. When it comes to I want to change my environment, I can unload the single module. This will remove Python, and when I execute command module list, there are no active modules. When I will do it, I will load. Sorry, I forgot. I loaded two modules. I can, with the unload command module unload, remove single module, but I can also completely clean my environment, completely unload all modules with the command module purge. And purge removes all loaded modules, and there are no modules active. You can try it by yourselves. It's quite simple how to use environment modules, so I will not talk more about it. Any questions?
think not, but Gordon, I suggest that we pause for about 2 minutes for people to catch up and to execute the commands by themselves, okay?
So let them run these commands for yourself.
Yes. Just for a few minutes, okay?
Okay, I'll
Catch your breath. There is still a lot ahead of us.
I'll put commands on the screen. Is it okay if I continue?
Hopefully, yes.
Okay. Now we have to say a little bit more about the Slurm, more than about the environment modules. In the first part, I was talking about the connecting to the supercomputer. And I mentioned that when you connect to the supercomputer, you are allowed to log only on login nodes. Actually, you don't log, you don't have access to the computational nodes. Slurm is a system that's responsible or in charge for find available resources for your calculation, execute them, release the resources for and resources that were engaged for your calculations, and return you the results. Actually, Slurm is most popular workload manager. A couple of years ago that I checked on top 500 list, it was on 2/3 of top supercomputing systems. So there is a lot of examples, a lot of literature, a lot of help on internet. So you will find a lot of materials about it. And also Slurm has also great and very detailed explanation on its homepage. This is what I mentioned. Actually, you are logged to login node, you prepare your calculation, your job on a login node, submit it to the Slurm. Slurm may find available resources, schedule it, run it, do the accounting, etc., and return the release the resources to other users or your calculations, and you will get your results. On the first looks quite complex, but it's very simple, almost like modules. Actually, what you need to know one command to run your job. You need 4 commands to have to work with the Slurm very easily, and more than these 4 commands that you see on the screen, you will probably not need more commands than these 4. From names, you can probably conclude what these 4 commands do. First one give some information about the systems and calculations. From now on, I will call calculation, I will call jobs. you will get information. First, S-info will give you information about the status of supercomputer and nodes. SQ will give you the status of current jobs, not previous jobs. S-batch will send your job to execution, and S-cancel will cancel your job that's already running on Bura or any other supercomputer. And you don't need more commands. Let's start with the S-info. You will get some output like this. You will get names of these are partitions. In the first column, there are partitions. Second column is if that partition is up or down, it is available or it's down for maintenance or etc. Time limit, infinitive. As I mentioned, we don't have limitations when it comes to the resources. No limitation for any of these partitions. And nodes, number of nodes, how much, what's the number of nodes that are in this state. Allocated means that they are completely allocated with jobs, with calculations. Idle means that they are not engaged in any job. Mix, it means that this 16 nodes are currently only partially used with the jobs. Drain is status when node is finishing some calculations and it's waiting for reboot or for a maintenance. Later I will say a couple of words about names and this partition. Partition is actually certain number of nodes that are put together and they are sharing same hardware characteristics. Any questions about this command, please run it. I will wait for 1 or 2 minutes so you can run your S-info command by yourself.
I think Katarzyna has a question.
Yes, hi. Could you explain once again what drain and DRNG mean?
This is drain. It's not in restart. No, it's drain is drain and non-responsive, that they are currently in restart.
Okay. And drain, it was that it's finishing the...
It's currently finishing, and this one is not responsive at this time. It's in
okay.
Since I wrote a script that after a certain time that nodes are up, some applications do not successfully release memory. So sometimes nodes restart.
Okay. Okay. Thank you so much.
Okay. Now the other after S-info. Okay, it's these are what are partitions. Now I'll say a couple of words about the partition. On Buddha, there are three main partitions called compute team, compute GPU, and compute SMP. What does this reflect? Actually, it reflects hardware configuration of Buddha. We have a main part of Buddha is a cluster. It consists of 288 nodes. Second partition, that's a group of nodes, is a GPU nodes. These are obviously nodes that have Tesla GPU accelerators. And we have two SMP nodes. These SMP nodes, we call them they are also called fat nodes since they have 256 physical cores. But more important is that each node has 6 terabytes of memory, working memory, no storage. And on which partition are you going to send your calculation? That depends on your problem that you are solving and application on your. Actually, if let's say primary and default partition, if you don't specify on which partition you send, you will your job will end on a cluster partition. For a GPU or SMP, you have to specify. But obviously, it's nonsense to send the CPU job on a GPU nodes. That doesn't make sense. And SMP makes sense if your application requires quite a lot of memory. Since in a cluster, each node has 2 CPU with 48 cores. That means 48 threads. Since hyper-threading is enabled, each node has 48 threads and 64 gigabytes of memory and its own SSD hard disk. On a picture on the right side, you can see how does it look like. And Buddha has altogether 188 nodes. Now you can see only 1/4 of Buddha is running. Since we are in a maintenance, we have to solve some issues with the cooling system, and it is summer and quite hot here. So only 1/4 is Buddha is running right now. SMP, as I mentioned, 256 physical cores and 6 terabytes of nodes on each of these 2 fat nodes. And GPU, they are not available right now. They are in a part of Buddha that's shut down right now. And each node has 2 Tesla car 40 or 80 per node. I hope that we will leave this nodes off, and we will make upgrade soon and install some new GPUs. Good thing is that Buddha, all these 3 hardware architectures, they share same storage, actually 2 storages. One is home and a scratch. Home is smaller and it's also slower. It altogether has 13 terabytes of memory shared by all the users. And Scratch has available altogether 1 petabyte, but to the users only 868 terabytes are available to users. Rest is used by system. Scratch is much faster since it has altogether almost 1,000 hard disks to have such a good performance. And when I'm talking about storage, I have to mention that I have to ask you, please don't use Bura storage as a storage. Simply take care of other users. And other thing is there is a very, very low redundancy level on a Scratch. It is big, it is fast, but it has a very low redundancy when it comes to the data. So in case Scratch can be deleted, it can, in case of any problem, there is no redundancy, it's not suitable for long-time storage. Simple as that. Upload your data to Bura, run your job, run your calculations. When you finish, download the results and remove rest of the data. Bura is, I also have to mention, is quite, has a quite fast network. Is based on InfiniBand. It's a FAT3 topology that enables quite engagement, quite a lot of nodes on a single job. I tested Gromax on more than 100 nodes, and performance with adding new nodes, performance was still going up. Since Bura is acquired from Bull, altogether with the storage is quite optimized by Bull, so very, very energy efficient and fast system. Maybe CPUs are not new, they are quite old, but it's a well-tuned. Well, actually, I have to mention this, that we were listed on a top 500 list. We were on a number 488, but I'm especially proud that we were on a 175 list, on the green top 5 list. That means energy, that list represents energy efficiency of supercomputer systems. But let's get back, let's go back to the partitions. As I mentioned, these are 3 main hardware or types of hardware on Bura, but there can be also some custom partition, temporary partitions. As you can see, this is now the test partition. This is RC232 partition. They are temporary. I bring them up for special purposes and remove them when I don't need them or when the users don't need them anymore. These are compute team, compute SMP, and compute GPU. That's the name test right now. These are 3 main partitions or a group of hardware on Bura. Okay, next command that we'll talk about, it's SQ. What does it do? It will give us information about the status of currently running jobs. Yes. It's a better. Can you see this screen?
Yes, we can. But the font size is really small.
Yeah. It's better on
Yes.
browser,
Yes.
but it's I have a problem with the zooming. So I will just this command SQL will just this command show you the screen. These are currently running jobs on this supercomputer. As you can see, first column says job ID, and each job is when it starts, it's assigned with its unique job. It is assigned by the Slurm. It's like ID of a job. It's numerical. On which partition is it running? Next column is partition compute SMP, I don't know, compute Tino, etc. Name, you can name your job. You can name your job whatever you want. User that started this job. This is running time of job. Let's say this job is running for 17 hours, 15 minutes, and 50 seconds. It's running on a single node, on a partition compute T, on a node named Bura 120. Let's say this job with its unique ID number running on partition compute T with the name TSO 8, etc. It's run by user a baggage, probably, and the current status is running. R stands for running job. It's running for 8 hours, almost 9 hours now, and this job is running on 10 nodes right now. SQ. You can also check running jobs per user or per partition. Using P parameter and partition name, I just got the list. It retrieved me nodes information about the jobs running on this partition. I can use also per user. Sorry. And it listed me all the jobs of user baggage that were sent to the execution. As you can see, this job has a pending status since this node Bura 44 is in reboot right now, and the job is waiting for that job to become available again. And here are statuses of a job: completed, completing, failed, pending, running, suspended, stop. These are also statuses that job we can have. Completed is already finished. Completing, Slurm is releasing the resources, etc. Failed, job failed. It will also give you short explanation why your job failed. If you requested unavailable resources or unavailable configuration. Okay. As cancel. This with this command you can cancel job. Here I usually get some question. Can user cancel job of another user? No, it cannot. only system administrator, or that would be me, I can cancel other user jobs. But in this 10 years, I did it only two or three times, but they were wrongly submitted. This is why that information job ID is important. You can cancel your job, single job. You have to specify job ID. Since one job can have only one ID, it's a unique, it's a single ID. You have, if you want to cancel that job, you cannot cancel it by its name. You have to specify job ID. Since multiple jobs can have same name, but they cannot have same ID. But you can also cancel jobs for yourself. All jobs that you are currently running, you can use minus U and specify your username, and it will cancel all your jobs. You can try to cancel other users' jobs. You can do it, but let's start with talk about sbatch, most important command. It says how to run a script. Sorry, I forgot to translate this from Croatian. Actually, there are two ways how to run jobs. Simplest and most used way to start calculation of jobs is using a script. You can also use sbatch with a single line. But in that line, you will have to specify all the parameters that are within a script file. And that line can be long for a couple of lines. Too complicated, too many places to make error, syntax error or whatever. I personally admit that I used command line to submit jobs. I use it only for testing purposes, not more than 2 times in my whole life. I'm using a script file. Why this is better? Once when you write a Slurm script, you can very easily use it again. Just rename it, change a couple of lines. It's much more faster than writing whole command line. So how does it how Slurm script looks like? In your home folder, you can find scripts, sample of scripts. I will go to some folder of some user. Here is some SC. This is example of one simple script. In this script, you just describe what you want. Name your jobs, and that's it. This information to Slurm start with this hash and sbatch. When Slurm sees this command at the beginning of line, it recognizes it as command or information to Slurm. Does anyone of you have some experience with the Linux? What this line, first line, does that ring a bell? What does it look like?
Yes, I can answer that. That first line is simply to tell the computer what under what syntax and shell the script should be executed under. Strictly speaking, it's not strictly necessary, but if you don't have it at the top of the script like that, you then, when you call it, you need to explicitly tell the shell what shell to run it under. So for example, if you didn't have /bin/bash at the stop of the shell, you would have to start a bash shell and then source the script.
Actually, you see this, this is the first line. That means the Slurm file, Slurm configuration file is actually bash script.
Exactly. Yeah.
That contain informations to Slurm. Simple as that.
It's best practice to have that at the top of your script.
Yeah, definitely best practice. But this is actually Slurm part. But let's go back. How do you start a job? SBatch and a script name or file name with that information. These are actually parameters, most used parameters for a Slurm. These are informational, job name, etc. But yeah, here you can see better. Job name. Here you can name your job. Otherwise, Slurm will generate some name with the numbers, combining job ID, etc. That's unreadable for human beings. So it's a good custom to give names to your jobs. Output. What does this command do? Actually, as I mentioned, when you connect to the supercomputer, you are connected only to login node, not to the actual computational resources or computational nodes that are running your jobs. And most of the code is generating some output to the screen. And obviously you cannot see that on your screen, but all the output to the screen of your code that's currently running is saved to this file, named ekran of the text there. You can also name, specify the error file. That means all the errors, regardless of Slurm, not errors of regarding of your software. Errors only regarding the Slurm will be written to this file greshka.txt. Otherwise, if you don't specify this parameter error, all will be written to the output file. But it's a good custom to also specify this error parameter. Actually, you specify it one and you can recycle your script for a number of times. Partition. This command, this is information for Slurm, what partition to engage, on which partition to send your job. Default is partition compute team on Bura. If you omit this parameter, it will run on a compute team. But it's also good custom to write this information, to have this information in your script. Oh, here's one line twice. This is my mistake. And this is a task. How many tasks are you sending to the computational resources, and how much memory per task? Here I deliberately didn't specify number of cores. By the default, Slurm will run this on one core if I don't specify number of cores. Default is one core. And on Slurm, I have to mention Slurm doesn't make a difference between physical cores and threads. For Slurm, threads are for Slurm, CPU cores are actually threads. Here in the compute team, each node has 24 physical cores, but with enabled hyper-threading, there are 48 threads. And for Slurm, he is treating thread as a CPU. And here I reserved memory per one CPU, 1 GB. I can specify job memory for a whole job or for a CPU. This last parameter is it's not required by the Slurm, but I require you to put this line in your script. What this parameter times means. It's also called wall time in a PBS and others. It's wall time. That means that this is the time that you allow this job to run on a supercomputer. Actually, your job can, you can estimate that your job will run for 3 hours, but specify for job time 5 hours. Why? Because your job may freeze at a certain time, doesn't converge to meaningful results. That means it can engage and reserve resources for indefinite time. And we don't want to do it, you know, neither me as a system administrator, neither you as a user. So specify this, specify wall time within your Slurm script. If your job is supposed to run for 4 days, specify wall time 5 days, it's okay. But specify it with a certain reserve. There's also one good, let's say, advice. Avoid calling another bash script from a Slurm script. Well, I will not explain it right now, but avoid calling. If you need to call another script, it would be better if you copy paste that script within this Slurm script. Let's do one simple script. We can run it on Bura just for how to do it. No, I will do it without, so you can. Okay, here I have a, oh, so, I entered someone, just a second. so that I don't interrupt someone session. Oh. No, finding security. How to run a script as batch in the name of that script. As you can see, my job is running. I am currently logged as a user edu40. What does this script do? Just sleep is just waiting for 240 seconds. With the rescue, you can check running jobs. Actually, this command, this sbatch, is the only one command needed to run your job. All other jobs are informational or optional. You need only one job, only one command to run your command. Actually, you can, you don't have to work in Linux text editor to edit textual files. How to do it? Here is a bitwise SSH client. I have this option, file, let's say file explorer or file transfer option within bitwise. And I will go to home folder. edu40. And here I'm in my home folder. And this is the script that I ran a couple of minutes ago. And I can edit this file within a Windows. I don't need to. I will, let's say, I will save this. Get out and check in my Linux. Oh, sorry. I'm in the wrong window. I'll check again. I'll check my file SC. As you see, this is a text that I changed within a simple Notepad Windows editor. That means on using a bitwise SSH client and VPN connection, you need to know only one connection, only one command to work on a Bura. There is also, say, this is how to transfer files. This is my, let's say I will go to my C drive. This, I'm currently working on a Windows. I will make a new folder, file from Bura. I created this folder. And how to copy these files? Just a simple drag and drop. I selected the files, drag and drop. That's as simple as that. Also, I can change properties of a file here. You can change also the permissions. So all of you who are more familiar with the Windows and you have a limited knowledge about the Linux, you have to know only one command, sbatch, and all the other things like file editing or moving files, copying files, deleting files, you can do it within a Windows or more familiar environment. Okay. Any question? Since I don't see the text and messages, if you have any questions, feel please speak, don't write.
Sorry, do we have to cancel the job that we've assigned?
No.
Because I can see like in the top that it is running still, so maybe I should cancel it. I don't know.
Just a second, it's running. Where it is running? No. Write SQ command again.
Okay.
If your job completes successfully before wall time, it will end regularly. It will inform Slurm that it has finished, and the Slurm will release resources and make them available to other users. As I can see.
Okay, right. Yes, true. Like it's finished already. Okay, thank you.
Just a second. You can specify memory in two ways: memory per one CPU, that's a thread in actual Nobura, or you can specify memory for a whole job. You can specify 16 gigabytes of memory for per one job. Or you can engage or reserve a whole memory of certain nodes. I will show how to do it later. Let's say more advanced is how to submit multi-thread jobs. That means jobs that are engaging more than one thread. Here writes again, what to have to point again. CPU here means thread. I am submitting one task.
Gordon, sorry to interrupt, but there's a question in the chat.
So sorry, I don't see the chat.
Sure. Marcus, do you have a microphone, or would you like me to relay the question?
Thank you. Yes. So after submitting a job with SBatch, do we have to maintain the SSH connection, or can we disconnect?
No, definitely not.
Okay, thank you. So we can disconnect.
No, job can run for around 15 days. It will, when it finishes, it will finish. Simple as that. But you don't have to maintain connection. For security reasons, I limited connection time of SSH connection to 8 hours. After 8 or 20 hours, well, I think 8 hours. That was a long time ago, so I don't remember exactly. But it's 8 after 8 or 12 hours, your connection, SSH connection, will end. But your jobs that are currently running will continue to run.
Okay, great. Thank you.
Okay, no problem. Here, only one difference between the previous single core script is number of CPU that I reserve for this calculation or this job. But keep in mind that there are always new users who have I don't know, single core calculation, single core program that was specifically written for one single core, and they try to reserve I don't know, 8 cores. that will not happen. That will no influence. That will not have any influence on time of execution. You are simply reserving more jobs, more cores that you need. You will reserve for your job 8 cores, but actually you will still use one single job. That means if you are using multi-thread jobs, you have to have an application that's capable to use all resources. When it comes to resources, you will find in Slurm literature, Slurm help, there's a term consumable resources. That means resources that you can specify in your Slurm script. Some supercomputers allow you to only specify number of cores. On Bura, I think that's using memory and CPU, using both of them for consumable resources, that makes Bura more efficiently used. So in your scripts, please specify memory and a number of CPUs. Just a second. Oh, sorry, I don't know how, but we get back. First example of script is MPI job or job that uses multiple nodes at the same time. That means multiple servers and at the same time. This is example of one such a script. Nodes means number of nodes that you want to reserve for your job. Exclusive means that you are exclusively requesting whole 12 nodes exclusively for yourself. That you will be single user on that nodes. Let's go back here on this. Just a second. Here we have some info. These nodes are shared, have a mixed status. That means that multiple users or multiple jobs are running on 17 nodes. Specifying this command exclusive, we are reserving whole this 12 nodes exclusively for yourself. This is a number of tasks for how many tasks, how many altogether, how many tasks per nodes, and how many CPUs per one task are engaged. Let's go back to this Slurm Gromax example that I mentioned earlier. Here you can see how much using specific right configuration for your software how much can this influence on speed of your job, how fast it will run on the board. More than 10 times faster, no, see. How much is this? This is 50% faster. On the same number of nodes, if I choose right combination of task and course engaged per one MPI task, that means that my job will run faster than this default configuration. But I'm familiar with the term MPI. This is a standard language for a communication with the among nodes that are running same job. Here I engage 12 nodes that are working on the same problem. They're solving same calculation, solving same problem. Obviously, they need to exchange some data among themselves, among these 48 tasks and these 48, let's say, points have to communicate among selves. So MPI is language, a standardized language for communication between tasks. This slide you will have here in your documentation. Directive that and directive explanation of that directive. Nodes means how many servers you will engage for your job. You will request. Exclusive, that means that you will exclusively that you request exclusive usage of all nodes. CPU per tasks, how many threads, no CPU is Slurm term, how many threads are required per task. And you can also specify task per node. Okay, any question? Your accounts will be accessible till the end of the month. So you to the end of the August. So you can try all these examples by yourself. You have samples of MPI script of multi-core. This is multi-core. So you can try them on Bura. And when it comes to the MPI, I have to mention Avail MPI. You have a. I'll switch to this. Many versions of MPI, from Muppet, from Intel MPI, Open MPI. Find that's suitable for your application, that's work best with your application. Many versions of MPI, so find the right one for your application. If you have an option to choose which one to choose, my recommendation would be definitely Intel MPI. It's quite similar to Muppet, but it's most optimized code of all MPI versions, let's say flavors right now in the market. Okay. There is no example of job array option. What does this Slurm script do? Crucial is this line that says array 1 to 50. That means that I can run 50 jobs with a single script. And the rest is specification, like for a single job. But crucial is, I will emphasize this again. Crucial is this line. We say array 1 to 50. I'm submitting 50 jobs with a single script. But the first one that looks like doesn't make sense. That means that my single Slurm job will run 50 times. That doesn't make sense. Makes sense since you have since you can also in the Slurm use variables. This here is an example how you can use this variables. Slurm array task ID. This is a variable that has a numerical value. It's a value of current running job. How can you use this? You can use this variable as a part of your input or output file. Okay, I will not go detail. I will not talk detail about this topic about the job array. Most users will not use it anyway, but those who do, they find it very useful since they don't have to submit Slurm jobs for 100 of times. They can do it with a single Slurm, with a single Slurm script. One good advice is put this code in your Slurm script. It will help you later tracking what's going on wrong with your code with the Slurm script. Also, you can provide this information to the system administrator. It will it will be later more easier to find where is the source of the problem. First line, this means start time. It will just simply put in the output file time when your job started. The other second line will put in output file name of your job, node list. It will put in output file names or all nodes that were used for this job. Number of nodes. This is if I engage engage five nodes, this line it will return number 5. Number of tasks, etc. It's a good custom to put this couple of lines in your Slurm script. You will put them once and use them multiple times. So it's a good custom to do it. When it comes to the scheduling, in Slurm, Slurm has the option to let's say to play with the priority, but in Bura, we don't have any user prioritization. That means first job in, first job out. First job that was submitted, it will be first in line to start. Even I don't have any prioritization on Bura. For all those who are going to work on a Bura, there is one useful command that's not part of Slurm. It's not official Slurm command. It's snode. What does it do? Let's see some jobs. Here, let's say Bura 170 is engaged in this job. And Bura. This command will return you the status of this node, detailed information of this job. Current status is mixed. CPU load is 47.1%. CPU allocation allocated only 24 threads of totally 48. Idle 24, and in another state there is none CPU thread. And this line returns how much free memory this node has, how much memory is left. Not much, obviously. Probably this user is using very wisely, engaging resources. For other job, same. But this command works only on Bura. It's okay. And now a couple of useful features. We passed it. Job dependency. Quite a useful thing for many users. Well, you can start one job after another at a certain conditions. Or unconditionally, but with a certain condition, it's more meaningful, makes more meaningful. How do you do it? With a simple command options is minus dependency and argument. What here are arguments? Argument is after, and that means that the job that you submit with this as batch after previous jobs begin execution. After any job will start after a specific job have terminated. That means terminated means that it ended successfully, unsuccessfully, but it terminated. Sorry, after correct, this means that job corrected successfully in construct with the previous argument after any result, the job can fail. But the job, if you specify after any, job will run anyway. But if you use this option after correct, it will run only if previous job or job that you specify finished successfully, or you can start a job if previous job was unsuccessful. And this one, last one is singleton. That means that you can, if you specify this parameter, that there is one condition before that. For jobs that you have a singleton parameter, they have to have a same name. And with the singleton option, next job will start only with if a job with the same name submitted by the same user ended, regardless is successful or unsuccessful. When this makes sense. But most of the users don't submit one single job. They, I don't know, run one software to prepare data, other software to do the actual calculations. With this, you don't have to wait using dependency. You don't have to wait that phase of preparation of your data finished. You can, and it will start automatically when a previous phase is finished, and your data is prepared for main, say, main processing. You can also delay jobs. You can specify certain time. You can specify now, that means 1 hour from now. Second line, last line will say that this job will start within 6 months or January next year. Okay, job array, I also mentioned this. You have sometimes you can find Slurm feature called Slurm variables quite useful. You can find the whole list of variables on Slurm site. There are quite a lot of them, so I didn't put them. I didn't include them in this presentation, but you can find them on Slurm site. Since many, if I understand correctly, many of you will do actually some programming. Well, you can use these variables for your in your application or in your Slurm scripts. I already mentioned how to use bitwise to transfer files, to edit files. Actually, you can do it all these things within a Windows environment. And just with one single command, you can send your job to the execution. There was one question, but why I can't use, why I can install applications like in my own machine, Linux machine? That's only partially true. Red part is obviously not applicable in this environment. Since you are not super users, you cannot run commands as super users. But yes, you can install applications on Bura. You can you can install them into your home folder or Scratch folder. But you don't, since this is command used in Ubuntu, and this we are using Red Hat, syntax is a little bit different. This command is called yum, and you have to specify where you want to install this application. You can install it to your home folder. You have to specify later, modify environment variables like path, library, etc. But yes, you can install your desired software by command yum into your home folder. But you cannot do it, install it on the whole system as a super users, but you can install it in your home folder. And I forgot to mention, login nodes on Abura have access to the internet, in contrast to some other supercomputer resources. Yes, you can download files, you can install software directly from login nodes. How do I manage different versions of the same software? Use LMOD, that means module load, module available, module purge. And many users used to program in Python. It's quite challenging to set up environment or environments for your projects without affecting users. Well, in the latest versions of modules, I try to implement this feature, and pip and other commands will work, will install libraries within your home folder by default. So use latest versions of Python, latest versions of modules on Bura, and this virtual will work. Otherwise, you will have to use Python environment, virtual environments, or you can use command pip with the parameter user. This instructs pip to install libraries to your home folder. Or there is also option to use Conda or Mamba environments. This is also option. Yes, it can be used on a board. And this is it for today, at least for me. If you don't have any questions.
I think this would be the end for today for all of us, and this is an excellent presentation. Thank you, Gordon, so much for dedicating so much time. Yeah.
Yeah, actually, I have to apologize for all those who are listening to me, but usually this presentation, this workshop lasts for 4 or 5 hours. I try to put it in I don't know.
In 2 hours. Yes, it is a very compressed version, and it is obvious that there is a lot to cover more. But since we are doing this as an intro, then we have to rely to the participants on the participants to cover the rest on their own, or to go for a second workshop that we will probably organize sometime in the future for the advanced usage, because it is obviously a lot of information. So does anyone have any questions right now?
I don't know if I mentioned accounts will be available till the end of this month.
Whether you mentioned something available, sorry, you broke up for a second.
No, your these educational accounts are temporary accounts.
Yes, you mentioned that.
Yes.
Okay.
Well, we can read something with I don't know, Professor Jurkic.
Well, this is something for the participants. This is my camera here. This is something for the participants to think in their free time. I suggest that we wrap it up for today because it was a lot of information and I guess everyone needs rest. Most of all, Gordon, who's same as me, is in time zone that is nearing night now already. But to all the participants, we encourage you to practice this stuff on your own. So you have the link to the lessons where you have a lot of these materials covered in a little bit different form. I suspect that Gordon can also share his slides with us so that you could follow them on your own independently. And I suggest, okay, Gordon is about to show us some pretty dashboard with, I guess, Bura load. Am I correct? Pretty.
So sorry, didn't hear the last sentence.
Yeah, I just saw that you are opening some pretty dashboard with a map.
Yeah, actually, this is map of users that are currently logged on Ubura. Yeah, people from Chile, United States, India, Poland. Great.
This looks pretty impressive. And I'm actually taking a print screen for future references. Thank you.
Okay.
Okay. Let's finish.
For all of you and bye from me.
Yes. Let's finish for tonight. Thank you everyone who attended and who listened till the end. And we are waiting for you tomorrow at the same time for more practical exercises and some coding stuff. And this is it. See you tomorrow.
Okay.
Thank you for hosting us.
Thank you so much.
Thank you.
Bye. See you tomorrow.
Thank you. Bye.
Bye.
Bye-bye.
Okay. See you everyone. It went well.
See you. Bye-bye.
Bye-bye.